Hello everyone, my name is Suyash Gupta. I'm a PhD candidate at University of California, Davis, and I'm advised by Dr. Mohammad Sadoghi. And in this PhD workshop, I'll be presenting a snapshot of my thesis, Resilient and Scalable Architecture for Permission Blockchain Fabrics. So what is this thesis all about? This is about blockchain. What is blockchain? A blockchain is a linked list of blocks. Each block in the blockchain includes the hash of the previous block. Each block also includes client transactions. Why do we need blockchain? Well, blockchain comes from a theory which says, why should one person manage all the data? Can we give everyone right to make their decisions? Basically, blockchain promotes democracy, decentralization, authentication, and security. Give everyone the right to vote, give everyone the right to hold and manage their data. At the core of any blockchain application is a Byzantine fault-tolerant consensus protocol. This protocol ensures that all the participating replicas order all the client requests in the same manner. Most of the permission blockchain applications employ a protocol called as PBFT. PBFT was the first practical BFT implementation. It says that consensus among n replicas can be achieved, and of those n replicas, f can be Byzantine if n is greater than or equal to 3f plus 1. So let's have a look at PBFT. In this case, we have primary, and we are assuming n is equal to 4, and one of the replicas can be Byzantine. So the client sends this request to the primary. The primary takes this request, it basically assigns it a sequence number, and sends it as a pre-prepared message to all the other replicas. When a replica receives a pre-prepared message, it verifies that request, and then it agrees to support primary's order by sending a prepare message. Now each replica waits for 2f prepare messages. When a replica receives 2f prepare messages, it achieves a guarantee that there were at least a majority of other replicas who also received the similar request. In such a case, a replica now sends a commit message. Now a replica waits for 2f plus 1 commit messages. Why? This gives us a guarantee that there were at least a majority of replicas who also prepared this request. Finally, these replica now can execute the request and can reply to the client. Clearly, we can see that PBFT requires a lot of communication. In fact, it requires 3 phases of communication, of which 2 have quadratic communication complexity. Leading to this, there have been other several BFT protocols which have tried to improve consensus of PBFT's performance. And there was a protocol called Ziziva, which says, hey, we can depend on the client, and if you say there are no failures in the system, we can achieve linear consensus. But that is not obviously the best case because simple crash failures can also exist. Then there were protocols which said that, hey, we allow multiple primaries to change after every consensus. Will allow primaries to change, but there will be a lot of phases. That is good. Primaries can change frequently, but that will lead to high client latencies. There are some protocols which say, how about we basically make PBFT linear by using threshold signatures. But threshold signatures themselves are computationally expensive. Then some protocols say, how about we have a lot of replicas instead of 3f plus 1. But there are already 3f plus 1 replica. Having a larger number of replicas reduces scalability. Some protocols suggest using trusted component, but trusted component themselves can become a sink to failures. So what do we present in this thesis? We present a series of protocols. The first of them is a proof of execution protocol. It's a 3-phase linear protocol. It employs speculative execution. To achieve higher performance, it introduces out-of-order message processing. It does not depend on any clients or trusted component. So how does PoE works? We'll show a very simple state diagram for PoE in a system where there are 4 replicas and 1 can be bad. Well, the client sends a request, and the primary sends a pre-prepared message like PBFT. Now, once a replica gets a pre-prepared message, at this point in time, each replica creates a signature. They create a small sign share, and they send this sign share to the primary. Primary accumulates these sign shares into a threshold signature and sends that message to all the replicas. Now, at this very point of time, the replicas are ready to execute the request, and the consensus is completed for them, and they can reply to the client. So how did it differ from PBFT? First, there's no quadratic communication, clearly. Then secondly, it it like unlike existing protocols, PoE allows multiple requests to process at the same point in time. And moreover, suppose at this point we call this execution as speculative, and it is possible some replica does not get all the set of requests, or the primary basically equivocates, then PoE allows requests to be rolled back. So we thought of doing a test on its performance. And here are the results. As you can see, compared to protocols like Hotstep and Ziziva, which in case of a single failure, like Ziziva can fail, PoE achieves 24 times higher performance. While for a protocol like SBFT, it can achieve 72% higher performance. But then PoE only reduces a phase, and we want to achieve higher performance. One of the ways to do is that to introduce parallelism. Basically, we want to give all the replicas power to the primary. We are just leaning on the principles of blockchain. Run multiple parallel instances of BFT, and decentralization, basically saying that there will be always a set of requests which can be ordered. How do we do that? Well, we say that give us a BFT protocol as an input and tell us how many instances do you want to run parallel. Let Z be the number of instances that we want to run parallel. And RCC basically runs those set of instances in parallel. Each instance will perform its own BFT consensus. This BFT consensus could be PBFT, ZZWAS, SBFT, or PoE, any protocol. And then once every instance completes its consensus, a common order of requests is created. And the requests are then executed in this order, and the clients are sent to reply. So we thought of comparing the performance of RCC and seeing how does it perform in comparison to other protocols. And as you can see, compared to a protocol like Ziziva, which on a single failure do not perform any better, RCC can achieve 26 times higher performance. Okay, so we reduced one phase in PoE, we added parallelism in RCC, but now we want to scale to global settings. And for that, we have a protocol called GeoBFT, which coincidentally will be presented at VLDB. So what was our intuition while building GeoBFT? Well, existing BFT protocols do not scale to geography large distance. The problem with these protocols is these protocols are not topology aware. And blockchain requires decentralization. Now, how does GeoBFT work? So GeoBFT introduces the notion of clustering. What we say is that replicas which are nearby, they can be clustered together. And once you cluster these replicas together, now each cluster can run its own consensus. And finally, every cluster can exchange this thing. So let's have a look. So we have two clusters, C1 and C2, and each cluster has its own primary. We are assuming each cluster has 3F+1 replicas themselves, and each cluster has its own set of clients. And a client sends a request to the primary starts the PBFT protocol. So whatever the stages happen in PBFT, that's what is happening here. Now, at the end of this thing, each cluster has its own request replicated locally. They don't order it yet. They just replicated it. They got enough number of commit messages, and now they share a certificate with each other. So once they exchange this certificate with each other, now some of the replicas get this certificate, and then they share among in the whole cluster. Finally, each replica of the cluster has a certificate. Now they can go ahead, execute, and reply to their local clients. That is how GeoBFT works. The whole details about how the ordering can be done and why GeoBFT guarantees security can be seen in the paper. So to test all of these protocols, we used our system called as ResilientDB, which we call it as a high throughput yielding scalable permission blockchain fabric. ResilientDB will be presented at ICDCS this year, and it is open source for researchers and practitioners. What did we learn in ResilientDB? The whole idea behind ResilientDB was that we first tried to dissect existing permission blockchain systems, and we found inherent limitations in their design. We found most of these existing systems are either single-threaded and they have a monolithic design. They require successive phases of consensus to be run sequentially. They do not separate between ordering and execution. They have no discussion on off-chain, on-chain memory management, and employ expensive cryptographic practices. ResilientDB allows user to test and choose whichever practices suit their system. So this is the whole architecture of ResilientDB. As you can see, it's a layered architecture. It has a secure layer which provides all cryptographic functionalities, execution layer which provides threads for execution, for matching different type of messages. It has queues for each thread. It has a network layer which basically handles the message, and it has a storage layer for managing blockchain and the metadata required. So this was our idea about how ResilientDB works and how we try to ensure a permission blocking system can achieve high throughput. Now we try to see what are the existing or open problems which are still there, which we are trying to solve. First, GOT requires each cluster to order and execute all the requests. Can we employ data partitioning? Is it possible that we can employ some technique of sharded system? Existing sharded systems do exist, but they have expensive communication cost for multi-shard transaction. Is there a way we can achieve optimal communication in such sharded blockchains? Now, one of the main problems with most of the blocking system is that how to find malicious people or how to detect them. With the growth of machine learning techniques and data mining techniques, can we actually use them to predict which replica will act malicious? Can we decide on them, and can we eliminate them ahead of time? So these are some of the future open directions which we believe are in the permission blockchain, which any researcher can pick and try to solve. So apart from this, there are other works which are part of my thesis. I've also looked at designing of efficient commitment protocols and partition databases. We had an easy commit paper, which basically looked at two-phase non-block commit protocol. And we also made a geoscale version of that. We also tried to achieve efficient concurrency control in partition databases. For that, we had a queue store. So apart from that, finally, I will invite you all to meet us at VLDB 20. We'll be presenting our ResilientDB paper. We'll also be, if you want to learn more about consensus and see the details of all of the protocols, we're also presenting a tutorial about these things. And finally, we'll have a demo that will present ResilientDB in more details. Thank you.